Boom.
What is an equation?
What do an equation do?
Equation is just a relationship between things.
And on one side of the equal sign is the same as the other thing on the other side of the equal sign.
So let's go ahead and use some equations to talk about how we found our moment of inertia. So first question, how did we find the translational acceleration? That's linear acceleration.
Well, here's the data we took.
And this is the equation that you started with right here.
That.
And in order to find acceleration, we just 2d over t squared.
Yep.
We just got rid of that, right?
And the d would
y.
be the delta y.
Yeah. Boop, boop. So let's go ahead and do 2 times 0.73 meters divided by 16.44 seconds squared. Okay, so we've got 2 times 0.73 divided by 16.44 squared, and I get 0.005.
So the acceleration is 0.005 meters per second squared. All right.
Great.
So we found the acceleration.
How do we find the force of tension on the string as the mass dropped?
That's important.
Okay, well, here's our equation.
Notice the direction of the arrows here.
So we had our force net, which is mass and acceleration, right?
So we can get that by taking the mass, the little hanging down thing, which
what
is
was our mass?
0.2 kilograms.
0.2 kilograms. And our acceleration we just calculated.
0.005.
And that's going to be subtracted from the force of gravity, little hanging down thingy.
So now, let's go ahead and calculate what that's going to be.
Yeah, let's do it. Okay, so I'll just do it right here. The force of gravity, the little hanging down thingy, is going to be the mass, which is 0.2 kilograms, times, we'll just call it negative 10 meters per second squared. So the force of gravity is going to be a negative
2 newtons.
newtons.
So let's also find the that 0.21 times 0.005.
Oh, yeah.
Let's
do
find the net force. That's
So
the mass times the
0.2
acceleration.
Good call. And I get a 0.001.
0.001. And that's going to be negative.
And why is that? Well, because what direction is the acceleration?
The acceleration is down.
Negative. And newtons.
So you want to take the screen up and put the numbers in? You know, move the screen up.
Yeah. That's a good idea, actually. Come on. Okay, so we just said
the net
negative
force.
1 newtons.
And the force of gravity on the little hangy down thing.
That's negative 2 newtons.
Negative 2 newtons.
Okay.
So how can we find the force of tension?
Well, let's go ahead and move it over there. Yeah?
So you're going to have to subtract a negative.
Force of tension. So we're going to... Oh, wait.
If you subtract the negative, that's the same as adding it.
Yeah. Right? So it would
you
be
did
like...
it right.
Yeah. So you could just add it on both sides, basically. If you're confused about this, you could also just subtract the negative, which is the same thing as adding positive. So let me go ahead and plug this in my calculator. We've got negative 0.001 newtons.
Plus 2.
Plus 2 newtons. And this is going to equal my thing.
It's going to be 1.99. What?
2 minus... Oh, I guess that was negative 0.001 plus 2. 1.999. Which we call it 2?
1.9. So the force of tension is 0.9. Is that what you guys got, boys and girls?
1.999.
1.99.
So should we call it 2? Or should we keep it
No,
at 1?
you can't call it 2. It's 0.119. So that's the force of tension. Newtons. All right, so now we've got the force of tension. Put that down.
Oh, you know what? That's going to be behind the board. You see right there how it comes down?
Yeah.
I'll put it right here. Okay.
Let's pull the screen down and see what the next slides
Now,
say.
what's our next thing?
You guys understand how we found the force of tension?
How do we find the angular acceleration of the spinning T?
How do we do that?
Okay.
Well, go to the next slide.
Oh yeah, it's up there. I forget you got it all set up for us. So this is the equation that we originally used. It's our watt instead of our watt. And we solve for acceleration, so it's going to look just like this. Exactly the same as this, except for angular, the parallel universe. And in order to find this theta,
We have to take the length of the string divided by the radius of the pipe.
so let's go ahead and do that. So 2 times the string length is 0.73 meters divided by the radius, which is
point 0.0125.
yeah, radius. Oh, we should have written that down earlier. So radius is 0.0125
Half the
meters.
diameter.
0.0125 meters.
All over.
All over. I was like, wait, we're forgetting something. Our t, which is 16.44 seconds squared. So I'm gonna want to put, when I plug this in my calculator, Boykin,
Yeah.
do I want to? I can just plug it straight in.
I do 2.73 parentheses. Well, no, you should be able.
Right?
Yeah, 2 times 0.73 divided by 0.125, and
So
then divided by 16.44 squared, because you don't have anything complex in the denominator on either of the two fractions.
Okay, and I get, okay, this makes sense, 0.434.
0.434.
Oh, not meters, radians. Per
Second squared.
That never makes sense.
It does. So,
Okay.
so now we've got the angular acceleration.
And
What was the?
how do you find T?
Go to the next slide.
Oh, sorry.
The torque.
I forget, it's all on there. Because Mr. Boykin put together this amazing sequence here. So torque is force times the lever arm.
The lever arm is where? That's the radius.
That's gonna be our radius right there. What do you got on your next slide there?
No,
Oh,
no.
right. Okay, so our torque, well, our force of tension is right here. Our lever arm is right here, so we can find the torque by saying, where's the force? 1.999 newtons times 0.0125 meters. The torque is going to be 1.999 times 0.0125, and I get 0.025.
0.025. So that's the torque that the string is exerting on the pipe that's making the thing spin.
Yeah,
What was that thing we're trying to find now?
Yeah, what are we trying to find? So we are trying to find the moment of inertia. We're right here.
Yep.
Okay, moment of inertia, which equals the torque over the angular acceleration. We have our torque. Our torque is 0.0.
This is just Newton's second law applied to angular motion.
And our angular is 0.434
That's the acceleration.
radians per second squared. And for my answer, we're gonna get, so just divide that by 0.434, and I get 0.058.
0.058. Is that what you guys got, boys and girls?
Inertia equals 0.058, and these are kilograms meters squared.
Yep.
Okay, so that is the moment of inertia for this. Let's go ahead and talk about everything we just did. Okay, so our goal was to figure out the moment of inertia.
That was our goal.
And so in order to do that, we need the angular acceleration and the torque.
Yep.
I'm gonna work backward here.
I like that.
So in order to find the angular acceleration, we can use our kinematic parallel universe.
Yeah.
And so we end up using this equation right here to figure that out, to figure out our angular acceleration. How did we know what our delta theta was here?
That's an excellent question. We used the Rosetta Stone.
And this is just the string or the stripe on the ground, same thing. And our radius, our time we measured using our stopwatch.
Yeah.
Now for the torque, we had a few additional steps here. For the torque, that's the force of tension times the lever arm. And the lever arm is, as again, the radius.
The radius, that's
Right
the lever arm pulling on the string.
But the force of tension,
That's a little more complicated, and I think
we did that here. Okay, the force of tension, we did that here, and we had to think about, we have this sort of thing going on, right? We've got the force of gravity down and the force of tension up. Those are the forces that play. These two together equal the net force.
the net force.
And so we did that whole shebang, but how do we even know the net force? How do we know this? We had
Mass
to
times
find
acceleration.
the regular acceleration.
The linear acceleration, the regular acceleration, all right? And how did we do that?
Well, we measured the delta y. We know the initial velocity is 0. We measured the time. We were able to figure this out using this.
Yeah.
We plug that in. Force this number times the mass, which was 0.2 kilograms, and we get our answer here.
Now, an interesting thing, I like the way it's on the board. Notice we've got the angular acceleration above and the linear acceleration above and the angular acceleration below, and they're both calculated the same way.
Look at that. Same exact equation, just different plays.
So you're probably thinking to yourself, this is complicated. That's a lot of steps. But you know what? Life is complicated. Life is filled with a lot of steps.
Sometimes I struggle with this thing. Like
Here, let me show you. Pull it down.
it's just today's doing one. It's like, oh, there it is. There it is. Sometimes I don't know like what it's thinking.
Poltergeist!
I know. Well, you.
Where are we?
I think I got something in my eye. Okay, so I forgot. We're doing another one.
Okay, so boys and girls, let's do another using this little guy.
Stopwatch.
Meter stick.
The radius is going to be the same, right?
Yeah, the diameter is still 0.25, so the radius is going to be point.
And I'm going to guess that the height's going to be the same, but we'll just measure it anyways.
All right, so I'll hold on to it.
Okay. Oh, I'm going to go right here.
Yep.
Okay. Here we go. It's actually a little bit shorter. Okay, so it's 0.69.
Well, 0.69 is the delta y.
Okay.
So
and
write
turn
that
this
down.
on. So 0.69. In fact, you know what? Let me just write that down, because I also need to keep this in mind. Okay, we're gonna write these right here. Okay, the delta y is
9 meters.
0.69 meters. We're gonna find the time, and then the diameter or the radius is still
0.0125. It's half, yeah.
Okay. Let's find the time. On your marks, get set, go. I realize we're a little close to the table there with the string. And stop. Bada boom. What?
Down goes Fraser.
Down we go. Okay, 9.57 seconds.
Ooh, that's a little bit more than half as long as that one took.
Okay.
This one's like that.
So go ahead and do
like that.
it again.
So that's your challenge.
And now your homework is on page 242, you're gonna do number 13, and then 246, 35, and 37.